accelerate towards each other or away from each other, okay? So a common misapplication of Newton's third law is to accidentally attribute the action and the reaction onto the same thing. Of course, if you had, for every force that acted on an object, you had an equal and opposite force on the same object, nothing could ever feel a net force. But that's not what we're talking about here. We're talking about two different objects. They both feel one force, and they're perfectly capable of accelerating in response. Okay? All right. What else did I want to say about this? Oh, and let me give you one more example. Let's take two objects, a baseball and the entire Earth. All right. So we know that the baseball feels a force of gravity. That is what gives it the acceleration to fall down. And what Newton's third law says is that nothing can exert a force, even the Earth, without feeling an equal and opposite force back on itself. So there will be a force on the Earth. It's not smaller, it's not bigger, it's exactly the same size, opposite direction. So these two forces are equal. Let's go ahead. I'll call this lowercase m. I'll call this big M. So we can write small m, big A, equals, and let me not bother with the signs. Just do magnitudes here. Big M, small a. I guess this is the acceleration of the ball. This is the acceleration of the Earth. Now the acceleration of the ball we already know. How much is it? 9.8. This is our good old g. It equals 9.8 meters per second squared. The Earth does not accelerate at 9.8 meters per second squared. It's a drastically smaller acceleration, right? If you were to solve for it, you'd have to divide this stuff over here by the entire mass of the Earth. You get a tiny, tiny acceleration. But it is technically true that when you drop a baseball, it's not just that the ball falls down, it's that the ball and Earth fall together, okay? So the baseball moves down, accelerates downward, the Earth moves up to meet it, accelerates up to meet it. So let's try it. Did you see the Earth move up? Probably not, because the acceleration is tiny. And the Earth fell up about the billionth of a width of an atom, okay? So you probably can't see that with the naked eye, okay? But it is true that it did fall up, because the Earth cannot exert a force without feeling a force back on itself, okay? If there was something that was comparable to the size of the Earth that was falling towards it, they would actually much more visibly accelerate together. So for instance, with me in the chair, we're a lot more closer in mass, so you still see the chair accelerating more than I do, but you can see me move a little bit, right? Okay, so with that, let me go ahead and do an example. This is very similar to the homework, but it's something that definitely is very tricky. So I want to establish what the heck is going on. So here is my situation. I'm just going to hold the eraser at rest in my hand. Seemingly very simple situation. And let's analyze it. So let me draw the object. And then let me draw my hand. I don't mean to say that it's floating there, okay, above my hand, but it's going to be better if it's kind of like a little apart, okay? You know, it's like when you see those blueprints where you kind of see like that they're kind of splayed out so you can see all the parts. That's what I'm doing here, okay? I'm not throwing this, I'm just holding it in my hand. I just don't want to draw them smack on top of each other because that's going to be difficult. So what do I have? I have the force of gravity obviously pulls down on the object, and I have the force from my hand that holds it up. So here's my question to you. Are these forces opposite directions? Yes? Yes, they're opposite directions. Are they equal in size? Yes. Yes, they are. Are they an action-reaction pair? How many people say yes? How many people say no? How many people aren't sure? Okay. They are not an action-reaction pair. Yes, they're equal in size. Yes, they're opposite in direction. But that is not all that it takes to be an action-reaction pair. You can have forces that are coincidentally equal and opposite, but they don't have to be equal and opposite. My very first clue that these are not an action-reaction pair is that they are both acting on the same object. Okay? Same thing I was talking about with the person who's trying to make up an excuse why they can't get up. Okay? Both a force and its action-reaction pair will never wind up on the same thing. Remember, these two always act on different things, and I have two forces on the same thing. So these two forces, you might get tricked into thinking they're a pair because they have certain features, but if they're not a pair with each other, let's find their each partner. The best way to do that is to write down what the force it acts on and where it comes from. So I'll go over here. This is the force on the eraser from, where does that force of gravity come from? What does that pulling? It's the Earth, right? So those are the two objects involved. You can just read it, right? This is a eraser-Earth interaction. Where's the pair? Well, we just did this actually, right? It's the same as the example I just did with the baseball falling down. It's on the Earth. If the eraser gets pulled down by the Earth gets pulled up by the eraser. So the action-reaction pair is the force on the Earth from the eraser. I just reversed the two words in the sentence, and there is my interaction, my action-reaction pair. So I'll label these guys action-reaction. Those two are always equal and opposite. They either both forces exist or neither exists. If one is whatever size one is, the other one always has to be the same size. They're an action-reaction pair. Right? Well, let's find the pair for the other one. I should probably label it a different color now that I know it's not a pair with the force of gravity. So what I have here is my first pair is in green, and my second pair is going to not be. I guess I should label this as well. The label should be in a different color. Let's figure out what this is. This is the force on the eraser from what? The hand. So this is speaking to an eraser and hand interaction. So I can put down its pair. Looks like that. You can see why I splayed these guys out now. Okay. So if the hand pushes up on the eraser pushes down on the hand. That's an action-reaction pair. So I actually have one each of these. Gravity is attractive, and the normal force interaction is repulsive, right? So the two arrows here, whatever color this is, pink or whatever, those are apart, right? Let me write this down. This is the force on the hand from the eraser. That's a pair. Those forces either both exist or not. They are always the same size no matter what. So there is all of the interactions that are going on that involve the eraser. I could, of course, also put in an action-reaction pair between the hand and the earth, but let's leave it there. Everything interacts with everything, and we go too far down the rabbit hole. So the first two that I started with were not a pair, okay? They just sort of looked like a pair, but in fact, those two forces that act on the eraser come from the fact that the eraser interacts with two things in the outside world. One is my hand, and one is the entire Earth. Now, in this problem, most likely, I would cordon off this part of the world as my object, right? So that's the thing that I perhaps would care about figuring out. What does it do or doesn't do, okay? And then everything outside is my environment, right? So I might make an artificial distinction about cordoning off one object to examine, and then I go ahead and everything else is the environment, okay? So when you're using Newton's second law, what goes into F net are halves of action-reaction pairs, okay? So you are listing all the different ways that this object is being affected by the environment, but you don't care about the other part, which is how this object in turn affects the environment, right? I'm not trying to calculate anything about the hand, right? I'm not trying to calculate anything about the Earth. So the only function that the hand and Earth play in this problem is how they interact with the object of interest, which is the eraser, okay? So I'm gathering up those halves of action-reaction pairs to figure out how the environment affects the object of interest, okay? Now, if you need further proof that the original two forces weren't an action-reaction pair, let me point out that I can easily accelerate this thing upward, right? Which means that I push up on it harder than gravity pulls down. So I can decide, for instance, to not hold it in place. I can decide to push up on it harder, right? Then the net force would just be this minus this, and I'd have something left over, right? But if I increase this, which of these two has to increase as well? It's the other pink one, right? That's the pair. So this, the two pink are action-reaction pairs, so they always go together. So if I push up harder on the brick will push down harder on my hand. The force of gravity that pulls down on the brick or eraser or whatever it is, the force of gravity is still the same as it was. And so the force up on the Earth is the same as before. The green arrows don't change. I'm just deciding to change the pink ones, right? Does that make sense? So the green ones aren't going to change because I assure you the Earth doesn't care if I'm lifting the eraser or not. The Earth pulls on it all the same. Okay, are there any questions on that? Yeah. It's going to push harder on you're going to feel a larger force on your hand as well, right? If you decide to accelerate it upward, which means you have to push on it harder, and gravity pulls down on it, if you push up on it harder, it pushes down on your hand harder. Oh yeah, like, you know, you can try it if you want, like, grab an object and you'll get a sense of how much force you need to hold it in place. If you want to then try to accelerate it, right, in any fashion, you're going to find that the force required is, you feel much more force back on your hand, right? Because that's because you're exerting a larger force onto the object, it's going to exert a larger force on you, right? Are there any other questions? Okay, so that takes care of Newton's third law. So we're ready to come back to this over here. And what I'm going to start doing for the moment is, of course, working backwards one step at a time. Let's talk about how to combine individual forces into a net force. Okay? individual forces into a net force. I'm going to start slow and move to the most general and most complicated case. I'm going to have two force magnitudes, 3 newtons and 4 newtons. These are just the magnitudes, but I'm going to take liberty with which directions they point. And I guess let me give you that the mass of the object that I'm going to be exerting them on is 2 kilograms. And I'm going to go ahead and start with the most simple proposition, which is that the two forces are exactly pointed the same way. So then you could probably easily imagine that the amount of net force is what? 7. You just add them. That's it. They're totally helping each other out. No drop of force is gone. None wasted. Net force is 7 newtons to the right. And the acceleration, using Newton's second law, of course, I just divide the force by the mass, so 3.5 meters per second squared, and it's always in the same direction. All right. And I guess I should put the vector hats here. So these are vectors. Now let me try it like this. Let me have them go directly against each other. So now instead of totally reinforcing, they're totally opposite directions. How much net force do you think we're going to have left over now? 1 newton, right? It's just the difference. So one pulls forward 4 newtons, but the other one takes 3 of those away by pulling oppositely. We only have 1 newton left to the right. Half net equals 1 newton to the right. And of course, now that the environmental influence is much smaller overall, we're not going to have as much acceleration. The net force divided by the mass, our acceleration is only going to be 0.5 meters per second squared, far less. Okay? So that's all one-dimensional, where you're basically either adding or subtracting, but of course we've moved into 2 dimensions by now, so there are other possibilities. Let's say it looks like this. We could pull these 2 forces at 90 degrees, right? There's nothing stopping you from pulling 2 forces at 90 degrees to each other on an object. Well, this one is, again, we get a nice little special trick, because we can sort of imagine that F1 is like the x component of the net force. So that would be, I guess if I'm using our standard axes, this would be plus 3 newtons. I reassemble it. And I can kind of pretend like F2 is the y component. Because for whatever reason, whoever decided to pull these 2 forces like this had them pulling on completely independent axes, right? So the net force is going to look like this. How big is it? 5 newtons, right? If you remember from geometry, there's such a thing as a 3, 4, 5 triangle. If you don't believe me, you can use Pythagorean theorem. So the net force is 3 newtons. Oh, sorry, 5 newtons. By the way, the number kind of makes sense. It's not as big as it was when they were in the same direction, right? That's the top case. It's not 7 newtons. It's not as small as when they were directly pulling against each other. That's 1 newton. It's somewhere in between, right? Here we might also find the angle. We can use inverse tan for that. 3, 4, 5 triangle has nice round numbered lengths, but there's no special angle. Angle comes out to be about 53.1 degrees above horizontal is how I'll describe that. And then the acceleration, of course, same direction. And to get the amount of it, I just divide the net force amount by the mass. So that's 2.5 meters per second squared. So that's all well and good, but so far these are all tricks. Okay, these are all special cases where it's easier to get the answer than in general. So the forces happen to point exactly the same way, or exactly opposite, or exactly 90 degrees. You can pull these two forces however you want. So let's look at how we might do this in general. These are independent forces. We might have benefited from pretending that they were components of the net force, but these are completely independent forces that can make any angle to each other. Then it need not be 90. So let's imagine we had force 1 pulling at 30 degrees and force 2 pulling at 60 degrees from the horizontal. So how do we do something like that? So this is where we need to talk about the general process of vector addition. So how do we combine two vectors that are arbitrarily pointed, and how do we find out what is the overall force that they would exert? So here is what I will suggest. You do the exact same method that you do with assembling components. So components are kind of like mini vectors. They're like mini vectors that have to lie along a coordinate axis. What we learned, what you do is you put them head to tail, and then connect the tail of the first to the head of the last. We do the same thing with these. So again, we do the head to tail business. It looks like this. This is our 30 degrees. This is our 60 degrees. Notice that when I put them head to tail, I did not change the vector. If you make it longer or shorter, that's obviously bad news. It's also bad news if you're trying to move it head to tail with another one, you start rotating it by accident. Okay? Remember, the direction that a vector points is what makes it the vector that it is, right? So I've just moved spatially where the arrow is located, but I haven't changed. I took this arrow and I put it over here, but I didn't accidentally make it point somewhere else. So if I do that, this is my net force. Right? And I need to figure out how long is that and in what direction does it point. Now I'm not going to have time for showing you today, but let me give you a little bit of a preview on the answer. Okay? So I'm trying to figure out how many newtons is that and how many degrees above horizontal. Okay? I can put broad constraints on the answers so that based on my work over here on the right, so that I don't have to put all this stuff on the right-hand side back up on the board next time. So here's what I have. These two are more in the same direction than not. So I should probably get something. It's not going to be quite as big as 7. It's definitely not going to be as low as 1. It's not even going to be as low as 5. So on my range of values is 1 to 7. And I know that 5 is when they're perpendicular. So I'm expecting something between 5 and 7 newtons, right? These are sort of helping each other out, sort of in the same direction, but not quite, okay? And by the way, this is looking correct. Because if you add this length, 3 plus 4, this is slightly longer than the shortcut, right? So that is going to be slightly less than 7. And then the angle, of course, is going to be somewhere between 30 and 60. You can see that from the diagram already. It's steeper than 30, but it's not as steep as 60. So it's steeper than 30, but it's not as steep as 60, right? In fact, it's not even going to be, the midpoint is 45. It's going to be between 45 and 60. The reason it's going to be more towards 60 degrees than 30 degrees is because one of the forces is bigger, right? And it matters more. So that net force of these two is going to be somewhere in this direction, generally speaking. And I'm going to show you how to find how big that force is next time. So let's break there.